Hi, students. Welcome to this chapter on light and electromagnetic spectrum. Light is a wave. White light is made up of light of many wavelengths, all traveling at the same speed. The colors that you see in a rainbow, which you can remember as Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, those mix together to produce the white light that we see. And then when that white light passes through a prism, the prism separates those colors to show you what those colors are. Those different colors are present because of the different wavelengths. Light is a wave, and it is made up of different wavelengths, some short wavelengths, some long wavelengths. The violet end is the shortest wavelength, and the red end is the longest wavelength. And it is these different wavelengths which makes us see those different parts of the light as different colors. The speed of light is 299,792 kilometers per second. This is the speed in vacuum. When it goes through plastic, water, or glass, it has a different speed. This speed in vacuum is mostly important for us because we are going to be talking about astronomy, and there's so much empty space, vacuum, and light travels through that. So that's the most important thing. We will approximate this and make it into a number that is easy to remember. C is the letter used for speed of light, and 3 times 10 raised to the power 8 meters per second. This is the speed of light. If we write it in the scientific notation and turn it into the, if we write it in scientific notation and turn it into meters per second units. So this is a number that you will be expected to remember. There are many types of calculations that we'll do, and you will need to use this number. 3 times 10 to the 8 meters per second is the speed of light. Temperature and light in astronomy. So we know the temperature of the sun. We know the temperature of different stars. How do we know about those temperatures? So many astronomical objects are so far away that we couldn't take any kind of instrument to get their temperature. And there is actually a relation between temperature and light. Things that glow because of their own heat, like stars, their color is a representative of what their temperature is. The hotter they are, the more bluish their light is, and the less hot they are, the more orange or yellow their light is. In fact, there is a more precise gradation that can be seen, and we use that to figure out the temperature. As I said, the different colors are different wavelengths. The wavelengths of electromagnetic waves depend on the temperature. Normally, when we look at the night sky, we cannot see these different colors because our eye is not sensitive to detect the color when the brightness of the light is very low, such as the stars that we look in the night. But with cameras, we can capture those and we can see the different colors. Talking a little bit more about this, and as we are going to discuss this more, we want to improve our understanding of what heat and temperature is. Heat is a form of energy that flows from an object at high temperature to an object at low temperature. heat is stored as vibrations of molecules and atoms. So if some object is hot, then that means the molecules and atoms inside it are vibrating. And the hotter it is, the more strongly the molecules and atoms are vibrating. The other thing is, in astronomy, in order to understand these principles and to do calculations, we need to use a different unit of temperature, and that is called the Kelvin scale of temperature. The special thing with Kelvin scale of temperature is that there is no negative temperature in Kelvin. For example, if we use Fahrenheit, then some temperatures we will say are negative 20 Fahrenheit or something. Actually, there is nothing negative about that temperature. The only reason we call them negative is a certain temperature is deemed as 0 degree Fahrenheit. And so when you go lower than that, it's negative. That creates problems with understanding and calculating the temperatures in science and astronomy. So we have come up with a new scale of temperature, which is Kelvin scale of temperature. And that the absolute lowest temperature that is possible in the universe, that is given as 0 Kelvin. So that temperature is achieved at minus 273 degrees Celsius. But in kelvins, that is 0 Kelvin. If we need to convert between the two units, this is the formula. Temperature in Kelvin is equal to temperature in Celsius plus 273. As our understanding of light developed, there was a lot of confusion about if light is a wave or if it is a particle. Waves and particles have different properties. Waves undergo diffraction. I will link a video which will explain the properties of waves and how they do the diffraction. There is a particular experiment called the double slit experiment. And when we subject any kind of phenomena to the double slit experiment, that double slit experiment can give us a result whether the phenomena is a particle or if it is a wave. And when we subjected light to it, we found that it is in fact a wave. So when we try to understand the properties of light, we understand that it is a wave. It is actually an electromagnetic wave. So any kind of wave is a disturbance in a medium that travels throughout the medium. For example, if you throw a stone in the middle of a calm pond, then that stone will create a disturbance in the center of the pond. And that center part will go down, and then it will bounce back up, and it will do that a couple of times. And that oscillation gets transferred to the surface around it, and that disturbance travels outwards in a circular motion. And that is a wave on the surface of the water. So in the same way, when we talk, the air molecules oscillate back and forth, and those are sound waves. So every kind of wave, it produces oscillations in some kind of medium. Saying that light is an electromagnetic wave means that light travels by creating disturbance in the electric field and the magnetic field. So that is depicted here in this picture. The black arrow shows the direction of the flow of a ray of light. And it is composed of the electric field, which is depicted by the yellow color, and the magnetic field, which is depicted by the purple color, and they are perpendicular to each other. Now, there is property of the waves, which is called wavelength. So if you measure the distance from one crest to the other crest, then that is the wavelength. And it is represented by this Greek letter lambda. Okay, it looks like an upside down Y. This is what we call it. And this is how it is written. And this represents the wavelength. Okay, so different waves can have different wavelengths. So for example, the red part of the electromagnetic spectrum has a long wavelength. So we'll choose red here, and we will why isn't it? So the red wavelength would look something like this. On the other hand, if we go to the blue or the violet end of the spectrum, the wavelength is going to be short, and so it's going to have more smaller squiggles. And that is what is meant by the short wavelength and the long wavelength. There is another property of the light which is called, which is the frequency. It is denoted by another Greek letter, which is called nu. And when we combine those, then we get this formula, nu is equal to C over lambda. This formula can be written in another way. So frequency, we can express it with F also. And that is going to be more easy for you to remember. So C is equal to F lambda. C is equal to F lambda. So C is equal to F lambda. This is a formula that you need to know and be able to use. What generally happens is that for any kind of wave, there is a wavelength and there is a frequency. And one kind of question you will get is you will be provided the wavelength and you will have to calculate the frequency. So we can take this formula and we can rewrite it. And when we rewrite it, then it looks like this. F is equal to C divided by lambda. Okay, so for example, we might be given a certain wavelength. We might be told that a certain wavelength. So for example, the green laser that you must have seen, some people use it as a laser pointer for presentations. It has It has a wavelength of 500 nanometers, approximately 500 nanometers. So that's that. And then the speed of light, as I said in one of the earlier slides, is 3 times 10 to the 8 meters per second. Okay, so there is 3 times 10 to the 8 divided by 500 nanometers. Okay. Now this nanometer, nano means 10 to the power -9. Okay, so wherever you have 10 to the power -9 in your calculations, you can replace it with, wherever you have nano, you can replace it with 10 to the power -9. So times 10 to the power -9. So this is the calculation that you have to do, and you will get an answer. So if we do this calculation, you can use your calculator, though I will warn you that be careful how you do this calculation, especially when you plug in the 10 to the power -9 in the denominator. There's a chance to make an error. So preferably put brackets, put parentheses around this when you're doing this, punching in the numbers in your calculator. Okay, so and so the answer comes out to be 6 times 10 to the power 14 hertz. This is the number 6 times 10 to the power 14, and the unit in which we measure the frequency is hertz. In short, we write it like Hz. 6 times 10 to the power 14 hertz. So that is how that calculation is done. So here is the light spectrum, and actually the whole electromagnetic spectrum. So you may have heard about these different kinds of waves and rays, and except some particular kind of waves like sound waves and some others, they are not part of electromagnetic spectrum, but a lot of them are actually just part of electromagnetic spectrum, and the only thing different about them is their wavelength. Okay, so just like different wavelength causes different parts of light to look different colors, in the same way, it makes them have different properties. And even though the electromagnetic spectrum, the range is very big, there's only a small portion of it that we can see with our eyes. The rest are invisible to us. So the whole electromagnetic spectrum consists of gamma rays, X-rays, ultraviolet light, visible light, infrared, and radio waves. You will see that there are 2 scales written here, one on the top, one on the bottom. The one on the top is the frequency, and the one on the bottom is the wavelength. So as we go from gamma rays towards the radio waves, both the frequency and the wavelength change. On the left end of the gamma rays, the frequency are the highest and the wavelength is the smallest. The frequency and wavelength are inversely related. When one is high, the other is low, and vice versa. So for gamma rays, the frequency is very high, the wavelength is very low. As we move towards slightly lower frequency, the wavelength increases and we get to X-rays. Then we get to ultraviolet. Then we get to the visible spectrum, the parts of the electromagnetic waves that we can see with our eyes. Then beyond that is infrared, and then even further beyond that is radio waves. Why are we talking about this here? We are talking about this here that because even though we cannot see these other parts of the electromagnetic spectrum with our eyes, but we can make instruments, digital cameras and other kinds of cameras which can see these parts of the electromagnetic spectrum. And so when we are looking out in the sky, not only we use visible light, but we use infrared telescopes and ultraviolet telescopes and X-ray telescopes and gamma rays, and each one of them gives us a different view, which lets us learn more about the astronomy. Okay, revisiting the idea of the color. So when we look at the sky and we try to learn things about astronomy, the color plays a very important role. So when we are talking about sun and stars, this is something that I mentioned earlier, and we'll go into more detail. The temperature is what determines their color. The more hotter the star, the more blue or violet type its color is. The less hot the star, its color is more orange, yellow, orange, or red. Okay. However, planets do not glow because of their own light. They just reflect the light of the sun. And so there is a different mechanism. Their color is because of the material that is present on the planet. For example, Mars looks red because it has red soil, which has iron oxide in it. And Neptune looks blue because it has methane, and that methane has this characteristic color. Now, this is one very important section. And this is also a kind of question that I ask in the diagram question part of exams and tests. So please understand this and practice it. So here we try to understand scientific properties of light and try to understand how this produces some of these phenomena that we see in our natural world. For example, the sky is blue. Why is the sky blue? Astronauts who have landed on the moon, they find that the sky is pitch black, is dark. Even when they are on the side of the moon where the sun is overhead, they can see the sun. Still, the sky is dark. And sky is dark because the outer space is dark. But why is it that on Earth we have this lit up blue sky? It is because of the atmosphere, Earth's atmosphere. The light of the sun comes and hits the Earth's atmosphere, and then it diffuses into the whole atmosphere. The more scientific proper word for it is a scattering. So when you are explaining these phenomena, please remember to use the word scattering. Okay. So actually, first let's talk about why does the sun look yellow? Astronauts who have traveled outside the Earth's atmosphere and looked at the moon, they find that the sun's color is white, kind of like the background of the slide, but it looks yellow to us. Why is that? The reason for that is this. We have to first look at the different colors that make up the white light. Roy G. Biv. If we roughly break it up into two parts, the red, orange, and yellow are the long wavelength and low frequency parts, and the green, blue, indigo, violet are short wavelength and high frequency parts. So when they hit the atmosphere, they have different tendencies. The blue, indigo, violet get scattered very easily, whereas red, orange, yellow do not get scattered. that easily. Okay. Yeah, so when the sun's light, which is it is emitting white light because that is its color. When it hits the atmosphere, the blue portions of it get scattered into the atmosphere, making the sky blue. And so the remaining light that gets to our eyes and with which we can see how the sun looks like, it has some of the blue portions of it are missing, and it now has a greater participation of greater contribution of the orange, yellow, red portions. And so that whole mixture looks like the sun is yellow. And if you have noticed, even the color of the sun changes at different times of the day. As when the sun is overhead, it's yellow. As it starts to go towards sunset, it starts turning more and more dark yellow and then orange, and it could even be red. And so why is it red? When at midday, the sun is overhead, the light has to travel only a short distance. So only some of the blue portion is removed from it. But at sunset, the light has to travel a longer distance. And in that time, much more of the green, blue, indigo, violet is removed from the light. And so the contribution of red, orange, yellow is much higher. And that's why the sunsets look red. Okay, so you should understand that. Color as a measure of temperature. So earlier I said that that high temperature stars are more blue and the less hot stars are more orange or red. Okay, so that's just kind of a qualitative description, just saying this color is hot, this color is not hot, as hot, but actually we can look at the color in more detail and actually calculate an exact temperature. The way we do that is by using the Wien's law. And the Wien's law is lambda max is equal to 0.0029 over temperature in Kelvin. So when we want to do that calculation, we actually change it up a little bit. With your knowledge of algebra, you will see that the temperature, we can take it to the left-hand side and bring lambda to the right-hand side. So then it would look like this. Temperature is equal to 0.0029 divided by lambda max. Okay. So when we take the light coming from the sun, you know that we can use a prism to break up the white light into the different colors, right? So not only the different colors, but there's the ultraviolet and infrared as well. We can split it up, and we have instruments with which we can measure the intensity of the different colors, and then we can make a graph. So this graph is intensity versus the wavelength. So for example, if we take this graph, which has 5,800 Kelvin written on it, it shows which colors are more intense, which colors are less intense. And here you will see that approximately this peaks at this part here, which is near 500 nanometers. So that means the green color with the 500 nanometers has the greatest intensity. in the sunlight. Okay. So that wavelength is called lambda max, where this graph peaks is the lambda max. And for all stars, the graph will always look like a hill with one peak. And wherever that peak is, you can drop a perpendicular and see which wavelength it is at. And when you put it into the formula in place of lambda max and do the calculation, you will get the answer. So for example, in the case of the sun, this curve, which has 5,800 Kelvin written on it, this is for the sun. Here in the graph on the right, we have written it separately. We have made it separately, and you can see that the sun's curve has a peak at 500. So the lambda max for it is 500 nanometers. So we put that into that formula and do the calculation, and we end up with the temperature 5,800 kelvins. Again, when you do a calculation like this, remember that nanometer gets converted into 10 to the power -9. So that's how we determine the temperature of the stars. Some other star, which is hotter, will have a greater contribution. Its peak will shift towards the left. And so the lambda max will be at a shorter wavelength, for example, at the violet end. And so there you can see it is also marked by a higher temperature, 7,200 kelvins. So that is the Wien's law. Some other laws that relate to the light and which help us determine properties of stars. The second law is Stefan-Boltzmann law. So just to repeat, this first law, Wien's law, helps us determine the temperature of stars. And then this is the second law, Stefan-Boltzmann law, which helps us determine the radius of the stars. That one is all the steps involved in doing that are a little bit complicated, and you will learn it in more detail when you go to the chapter on stars. But here I will just hint that that's what it is used for, and I will only show you how to understand this law. So the main thing in this law is this formula, which says energy emitted is proportional to the fourth power of temperature. So what does that mean? So anything that is hot emits heat, especially stars. They are burning at very high temperatures, and so they are emitting heat. Now, if we compare two stars, let's say one, where we pick the sun, and the temperature of the sun is 5,800 Kelvin, and then another star which is quite hot, it looks blue, has double the temperature. So how fast would it emit the energy? An intuitive guess could be that it will emit energy at twice the rate, but that's not the case. The energy emitted is proportional to the fourth power of temperature. That means if we are comparing the sun and another star, then the heat of the energy emission from the second star will not be just 2 times the energy emission of the sun, but it will be 2 to the power 4 times. Okay, so 2 to the power 4 times is 2 times 2 times 2 times 2. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So 16 times. So a star which has twice the temperature of the sun will emit energy at a rate which is 16 times as faster, or as more 16 times how fast the sun emits the energy. So this is a principle that you have to understand, and this is a formula. In this chapter, you'll be asked, in the homework, you'll be asked to do some calculations, and you have to demonstrate this understanding. Overall, in the long run, we combine this with some other principles, and this helps us determining the radius of the stars. So even though when we look at the stars, all of them just look like points to us. So we cannot really look at them and measure how big they are. But with this process, we can determine their radius. Okay, so the sun's light can be broken up into the 7 colors that is called spectrum. The plural of spectrum is spectra. So actually, there are 3 types of spectra. First is continuous spectrum, which we are familiar with. Okay, heat, a heated filament or a glowing piece of iron in a blacksmith's forge are examples of continuous spectrum. So anything which is solid and it is heated so much that it starts to glow, it produces a continuous spectrum. However, if you take some gas and heat it so much that it starts to glow, then it produces this kind of spectrum, which is called absorption spectrum. And the special thing with it is that it has these dark lines at some of the places. Actually, sorry, I said that wrong. When the gas starts to glow, and we take that light and send it through a prism, it will split up into its colors, but those colors will not be continuous. There will be just some lines, some color lines that will appear, and that is called an emission spectrum. And which lines appear, those are going to be always the same for a particular gas, for a particular substance. So it is like a signature. It is like an autograph of that element. And we use this property to identify the elements. So first is continuous spectrum. The other is absorption continuous spectrum, the emission spectrum. And then the third one, as seen here on the left, is absorption spectrum. Suppose you are producing a continuous spectrum with the help of a heated piece of iron, but then you make it pass through a cold gas. That cold gas will then absorb those lines instead of emitting them. As you can see, those dark lines are in the same places as those colored lines are on the right. So the gas will demonstrate its signature either by absorbing or by emitting. In either case, it helps us identify the gas. So absorption spectrum and emission spectrum. Now, it turns out that the stars and the sun emit continuous spectrum. Stars are made up of gas. So one would say, why do they emit continuous spectrum when just on the earlier slide we said only solids emit continuous spectrum? However, if you see the point A, a hot, dense, glowing object, it could be a solid or dense gas. So stars are always so big that their gravity compresses the gases into dense formation, and so they emit continuous spectrum. So they emit continuous spectrum. And right, so So they emit continuous spectrum. Let's talk about the low density gas. In some situations when there is low density gas, and this is more common here on Earth in the different kinds of lightings. So sometimes we have mercury vapor lamps or other kinds of bulbs that have been used, the ones which have gases in them. The kind of light they emit, when you send it through a prism, then you would see this emission spectrum. And so here 4 elements are shown: hydrogen, neon, calcium, and strontium. And you can see all of them have like a different signature. So we can identify which elements are present. What is the importance of it? The importance of it is we can take the light coming from a certain star, we can send it through the prism, we can look at the details of the spectrum, and we can identify what chemicals, what substances are present on that star. So why do gases only emit these particular lines? Why don't they emit the full spectrum? That was a big question for scientists. And they wondered why that is the case. And that explanation was given by Bohr, who was a pioneer of quantum theory. And here is what happens. When the gases are hot, the electrons in them jump to higher orbits. For example, this is hydrogen atom. Hydrogen atom has only one proton and one electron. So the electron is in the lowest orbit, the ground orbit. And when it is hot, it absorbs the energy and goes to the second orbit or the third orbit, but it doesn't stay there for a long time. It jumps back to the second orbit or jumps back to the first orbit. And when it does that, it releases that energy. And because there are fixed orbits, the difference of energy between third orbit and the second orbit, or the difference of energy between third orbit and the first orbit, is fixed. And so every time a fixed amount of energy is emitted, and that fixed energy amounts to a certain wavelength, a certain wavelength photon, and a certain wavelength photon, always that same wavelength photon. And the same wavelength photon means the same color. Okay, not the whole gamut of the different colors. And that's why there's only a few lines that appear there. How do we use this? So let's look at the sun. So the surface of the sun, which is visible surface of the sun, which is called photosphere, it emits a continuous spectrum. But as it's getting away from the photosphere, there is an atmosphere of the sun which has a colder gas, like particularly hydrogen. And so it emits, it absorbs some of the wavelengths. And so it produces the remaining light, the absorption spectrum, as you will see on the right-hand side of the diagram. And then as it is coming to the Earth, it passes through the Earth's atmosphere before getting to the telescopes. And so lots of dark lines are introduced, and we analyze those dark lines to figure out what is present on the sun and what is present in the Earth's atmosphere. And especially these kinds of experiments are especially useful during a solar eclipse, because during a solar eclipse, we can also see the emission spectrum. And that especially helps us figure out what substances are present in the atmosphere of the sun. And actually, from one of those experiments, the gas helium was discovered. So the helium was first discovered on the sun. By doing this kind of experiment, we realized that there is a new element which we didn't know about before, and it was named helium. And then later on, we found it on Earth, and we started putting them into balloons, right? The gas is called helium because it was first found on the sun. Helios is name of the sun, and so it's associated. This element was associated with that. That's why it was called helium. Okay, Doppler effect. So you must have had experience of this Doppler effect when a train or a car is approaching you and blowing its horn. The sound appears to have a higher frequency, but when it is getting away from you, it has a lower frequency. That effect, so you can hear the difference in the pitch of the sound. First it's high pitch, then it's low pitch. That is the Doppler effect. Doppler effect is used a lot in science to learn a lot of things. The Doppler effect can also be used in astronomy. So these stars, they are emitting the light to us. We capture that light with telescopes, and we analyze it with the help of prisms by splitting it into colors and looking at the dark lines. If the star is moving towards us, or if it is moving away from us, that causes a Doppler effect. That causes a change in the frequency, and that change in frequency becomes apparent by the movement of these dark lines, these absorption lines, and how much these absorption lines shift can tell us how fast the star is moving. We have a formula for that. Plus, which way they move can tell us if the star is coming towards us or if it is going away from us. So in the center is at rest when there is no movement. But if the lines are shifting towards the blue end, that is called blue shift. And that happens when the star is moving towards us, when it is approaching us, okay, because wavelengths get short. On the other hand, if it is moving away from us, then a red shift happens. And so this is very important. Most of the galaxies and stars that we see in the outer space, most of them are red shifted. And so that means most of them are just going far away from us. And that is how it was discovered that the universe is expanding. So this is the formula for calculating the speed. With this, we can actually calculate the speed with which something is moving. So delta lambda over lambda 0 is equal to V over C. Delta lambda is the amount of red shift or blue shift, right? So here's what a question based on this would look like. So we will say that normally there is an absorption line which is, let's say, at 500 nanometers, okay? But we are looking at this particular star, and it is showing that same line to appear at, it is shifted. It is at 505 nanometers now. (505 nanometers). So first, let's look at this and determine if it's a red shift or a blue shift. So going from 500 to 505 nanometers means that the wavelength is getting bigger. A longer wavelength means the shift is towards the red end of the spectrum. So this is a red shift. And red shift. And so going away. Moving apart. So that's one thing we can tell just by looking at that. But how fast is it moving? For that, we look at this equation here, and we rewrite it in such a way as to solve for the v, which is the velocity. So let me write it here. I will move the c over to the other side. And so then this will look like, now the delta symbol. How do I make the delta symbol? I will just write small d. And, well, okay. I will have to use the drawing function to write this. So the equation becomes v is equal to delta lambda over lambda times c. So that's how it looks like. And now we plug in the numbers. Delta lambda is the amount of shift. So how much is the amount of shift? We are going from 500 to 505. So the shift is 5 nanometers. And this is the original wavelength, which is 500 nanometers. Here, it's the same unit on the top and bottom. In mathematics, when you have that situation, then you don't necessarily need to change the unit. Normally, I would have said replace that n with 10 to the power negative 9. But because they are on the top and the bottom, its effect is canceled. So we can forget about that. We don't have to worry about it. And this 5 over 500 turns into 1 over 100. And in this case, we don't actually need to plug in the value of c, which is 3 times 10 to the 8 meters per second, because many times it's more convenient to talk in terms of what fraction of a speed of light is certain velocity. So here we can say that this star is moving away from us at 100th the speed of light. Okay, so it's convenient to do that if we just keep it like c. But however, if somebody wanted an exact number in terms of meters per second, then you would put down the value of c, 3 times 10 to the 8 meters per second, and do the calculation. All right, so that's how we use this Doppler shift. We are almost towards the end of this chapter. And this is, the next slide is the last slide, I think. The inverse square law of radiation. So we know that the closer we are to some stars, the more intense brightness and heat is. So the sun is so hot and so bright, you are told not to look towards the sun, right? However, we can easily look at the night sky and admire all the stars. The stars are basically like other suns, or sun is another star. So why can't we look at the sun, but we can see thousands of stars in the night sky? Because their intensity is less. Why is their intensity less? because they are so far away. So we can kind of generally understand that the further away a source of light is, the less intense it is. But how can we make a formula out of it? So the formula of this is the inverse square law of radiation, inverse square law. And that you can, with this diagram, you can understand it very clearly. So here is a star, and let's say you are at a distance of 1 light years from it. There is a certain amount of energy that it is emitting, which is passing through this one square. So it is concentrated in that one square, so it's high intensity. At that point, the star would look quite bright. But if you go to a distance of 2 light years, now that same amount of energy and light is projected into this bigger square, which is equal to 4 squares of the initial size. And so the light gets distributed into 4 squares, and therefore the intensity becomes 1/4. Then if you go to 3 light years, then it goes through 9 squares and intensity becomes 1/9, right? In the same way, if you go to 4 light years, it will become 1/16. At 5 light years, it will become 1/25, and so on. So that's how the intensity changes with distance. What do we do with it? I told you that we can calculate the radius of stars. So actually, we combine this principle with the Stefan-Boltzmann law. So we look at some star, we see how bright it looks to us. With other experiments, it's called a parallax method. We can determine how far the star is, and we can sort of do a reverse calculation that even though this star being so far away from us doesn't look too bright, but if we know its distance, we can back calculate how bright it actually is. And then if we can figure out how bright it actually is, and then that we can combine with the Stefan-Boltzmann law, and that helps us calculate the radius of the star. Okay. So that brings us to the end of this chapter. In this, we learned the different properties of light and how we use the light that comes from the stars and planets to analyze that light and learn something about astronomy and the properties of those objects, those stars and planets.